solving. This is out of lesson 6-2. Probably 1 page, I would think, is all that we need. So lesson 6-2, and we're going to talk about solving a system of linear equations. Using substitution. And today's date is the 17th. I know that date. Okay, so first off, we've talked about substituting. What does that mean? What does it mean to substitute?
Just place something in, like if it gives you an X, just place it.
Okay, so it's taking something and putting it in the place of something else. Now, those two things, the thing that I'm replacing and the thing I'm replacing it with, have to have the same value, otherwise you can't really use replacement. So substitution is replacing a value with an expression equal to that value. So I think I'm going to give you a couple of tips and hints on this, using the strategy. I'm not sure I'm going to write down bullet by bullet what you need to do. We'll go through some examples. Maybe we'll add a little bit of notes at the examples. So, because I don't want to just say, hey, follow this. I want you guys to see it's really not that big of a deal how to do this. Now, I can tell you we have covered this already with Math 8, and the biggest problem they had was they weren't really good at solving equations from the earlier chapters. So if that was something that kind of plagued you earlier, it's going to come back and bite you a little bit now. So that's why, going back and reviewing how to solve basic equations is super important. So with substitution, here's a couple things. Why would I ever use this strategy? When is it going to be most effective? So I'm going to use this strategy when one or both of the equations, oh, maybe if I could write today, yikes, is solved for one variable. Now, I can force this to happen, and I can force it by solving an equation for one variable, but already there's a better strategy that I can use in that case, okay? So, again, I'm going to use this strategy when one or both of the equations is solved for one variable. Now, I am going to put this down here. This is not a recommendation, but you may have to do it on tonight's homework. If necessary, solve one equation for one variable. Okay, we don't need to solve both of them, we just need one of them. And then what we're going to do is have something like this. You may have something like this. So what this is saying is that x has exactly the same value as 2y plus 3. So x and 2y plus 3 are interchangeable. Okay, so if I see x, I can replace it or substitute in the 2y plus 3. And that's really all this process is. Because the reality is I can't solve an equation that has two unknowns. So the only way to solve an equation with two unknowns is to get the two unknowns down to one unknown. And substitution is one of those strategies. Okay. So when I know that these are equivalent to each other, so these are equivalent expressions, equal, valiant, we can say that's value, so they have equal values, equivalent expressions. So they mean the same thing. So I can substitute one for the other. Okay.
So I don't get, like, if you would put 2y plus 3, 4x.
Okay, you have to see it in action, and then you'll understand it's how it works. Okay, so let's launch into a problem and see it actually work. So the directions are going to ask you to solve. In today's strategy, we're not going to graph. I want you to use substitution. So it's going to ask you to use substitution. Substitution. To solve the system. So let's say we have y equals 2x plus 1, and we have 3x plus y equals negative 9. So straight away my brain says, oh, this is perfect for substitution because look at your first equation. Y is already by itself. Okay? True that I could get y by itself in the second equation, but I don't want to do extra steps if I can help it. So what I do is identify the variable that's by itself. I identify what has the same value as that y. That expression, 2x plus 1, has the same value as y. Then what I'm going to do is substitute that expression, 2x plus 1, in for y in the other equation. We don't substitute back into the same equation, then we get something that just cancels everything out, and that doesn't make sense. So what I just did is what I do every time. I circle up the value, I highlight the variable, I draw an arrow to where I'm going to substitute. So here's what my new equation looks like. 3x plus, and then I put in the 2x plus 1 in place of y. Equals negative 9. So remember, our original equation said y equals that 2x plus 1. That's what allows me to do that. So notice what happened. What's left in my equation variable-wise? Only x's, which is awesome. I can solve an equation with 1x. Here we go back into the chapter on solving equations. Now, did I need the parentheses? No, this is again a teaching moment, so I'm just showing you how I just substituted in for the y. Here's the replacement for it. So what I have is 3x plus 2y plus 1 equals negative 9. So I look for like terms. We have 3x and 2x, which is 5x. And then we have plus 1 equals negative 9. We subtract 1 from both sides, and we get 5x equals, signs are the same, so I add negative 10. And then we divide both sides by 5. And we get x equals negative 2. Now remember, the solution to a system is either 1 point, so an x-coordinate, y-coordinate, it is no solution, or it is infinitely many solutions. The only time when I'm solving algebraically that I'm not going to get a point is if in my solving the equations, all the variables are eliminated. Then it's up to me to interpret my result. Okay. So right now, I've got half of my answer. So how do I figure out the y-coordinate if I know the x-coordinate is negative 2? Brandon?
Don't you go back to y equals 2x plus 1 and plug it in for x?
Yeah, and then we're going to use the real word.
Substitute.
We're going to substitute, exactly. And now, Brandon instinctively said, let's just put it there, because I'm supposed to figure out what y is. That equation has y by itself. Let's solve it. The reality is I can plug that value for x, substitute that value of x into either original equations. But I'm going to be smart about it like Brandon was, and he says, I'm going to go to the one that already has a variable I need already by itself. So I get y equals 2 times the value of x, which is negative 2 plus 1. And then I just solve this. So I get y equals negative 4 plus 1. I get y equals negative 3. So basically what this is telling me is that in my system, those two lines would cross at the point negative 2, negative 3. Okay. Now, how do I check? I substitute in negative 3 for y, negative 2 for x, and see if I get something that's true. So I get negative 3 equals negative 4 plus 1. Negative 4 plus 1 is negative 3. Check. So what this says is that that ordered pair, -2, -3, satisfied the top equation. Let me see if it satisfies the second one. 3 times -2 plus -3. Question is, does that equal -9? So let's see, we get a -6 minus 3, -9. Signs are the same, so I add them up, and I get -9 equals -9. So check, it satisfies the second equation. So I'm confident that that's my answer. Certainly a lot more precise than graphing, right? And that's all that we do. Okay? Let's go ahead and let's do another one. I'm going to give you one this time where they're not quite as nice, but because our directions are not changing and we are only allowed to use substitution, how do we deal with it when the equation looks like this? X plus 2y equals 6. 3x minus 4y equals 28. So this is, for us, substitution, worst case scenario. I don't have an equation that already has a variable by itself. So I go to plan B. Is there a variable that doesn't have a coefficient in either of those equations? Yeah, which one? X. X in the first one. So what I'm going to do is solve that equation for x. And the reason why I'm choosing that, it's the fewer number of steps to get what I need. So all I do is subtract 2y from both sides. And it really doesn't matter how you write the results. You can make it 6 minus 2y or -2y plus 6. Really doesn't matter. Now that you have a variable that's alone, you identify it's x that's alone, and what's equivalent expression to it? 6 minus 2y. I'm going to take that 6 minus 2y, and I'm going to substitute it in for x in the other equation. Now, that was weird thing number one that you may have to contend with. You may have to alter one equation by solving it for one variable. Choose wisely. Okay? 2. Note that where I'm replacing the x, there's a coefficient in front of it. That's still there. So when I rewrite the second equation, it's now 3 times the quantity. This is why I get in the habit of always using the parentheses when I do my substitution. The quantity, 6 minus 2y, and then I write out the rest of the equation. Minus 4y equals 28. So then I distribute, and I get 18 minus 6y, and then write out the rest. Minus 4y equals 28. We talked about in the chapter on solving equations that if I have 3 terms per side, that means I have some like terms. So I notice that it's my y's in this case. So I get 18, signs are the same, so I add, and I get negative 10y equals 28. Now I need to do inverse operations to get the constants together, so I'm going to subtract 18 from both sides, and I get negative 10y equals 10. And then last is I'm going to divide both sides by the coefficient of the y, that negative 10, and I get y equals negative 1. So now I have half my answer. I have the y coordinate. So I'm going to substitute that back into either, and it's always best to go back to original. Now, of the 2 original equations, which one would be best to substitute in y equals negative 1 if I want to figure out what x is? They're both on top. Right or left? Okay, left. Why left, Michael A? You notice I'm trying to solve for x. X is alone. He doesn't have a coefficient. And the other one, I still would have to divide by 3. So I have 2 times the negative 1 equals 6. So I get x minus 2 equals 6. Add 2 to both sides. I get x equals 8. So then check. It only takes a couple seconds, but you know what? It's far better to take the time now than wait till you get your test back and see that you had it wrong. So, sure enough, it satisfies the first equation. Let's see if it satisfies the second one. 3 times 8 minus 4 times negative 1. And we want to see if that equals 28. So we get 24, signs are the same, so I get a positive 4 equals 28. So sure enough, 28 equals 28. So it satisfies, oops, this one, both. So that says, yep, what you have is a solution to your system. So I want to see, I got one more. I want you to see what happens when the answer is not an ordered pair. What is it going to look like when you're solving the equation so that you end up not getting an ordered pair? So we have y equals 2x minus 4. You have negative 6x plus 3y equals negative 12. So do we have a variable already by itself? Yeah, what do we have? Y. So the value of the expression that means the same thing as y is the 2x minus 4. That is going to get substituted in for the y in the other equation. So here's what we have. Negative 6x plus 3, and then in parentheses, we have the expression that means the same thing as y, 2x minus 4. And then that equals negative 12. So I'm going to have to distribute. I get positive 6x minus 12 equals minus 12. 3 terms say you got to look for some like terms. Ooh. What happens there? Negative 6x plus 6x. Yeah, they cancel out. So all you're left with, there's no variable. So when there's no variable, now we have to interpret our answer. So we ask that question. When does negative 12 equal negative 12? Since this is always true, think about what would translate into always true for an answer choice to a system. No, it wouldn't be one. Infinitely many solutions. All real numbers is what we used to get when we were solving equations. They were individual values. But when it comes to a system, we're looking for individual points. An x-coordinate paired with a y-coordinate. Okay? So this becomes infinitely many solutions. Now, let's ask this question. What could I do to verify that that's right? How could I check? Because I have nothing to substitute in. Philip?
Any number.
Well, I could do any number.
Like zeros.
Okay. Tell me when you were graphing and your answer was infinitely many solutions. What was true about your equations?
It'd be the same.
They were the same equation. So could we check to see if these equations are the same? Let's try that. So the first one's already solved for y, so let's take this guy and let's solve him for y. So we're going to add 6x to both sides. We get 3y equals 6x minus 12. Divide by 3. We get y equals 2x minus 4. Oh, bingo. Same line. So we do have mathematical ways of checking. Okay? So let me ask you this question. What would the end result be if you did substitution and the answer would be no solution?
It's not true.
Okay? So in a no solution situation, you would get a statement that's not true, like negative 6 equals 4. Okay, so this is never true. What would be your backup check to see if you're actually right? What could you do?
Mention I'm not the same one.
How? What is it that makes you get no solution?
They're parallel.
The lines are parallel. Well, what makes lines parallel? Two things, same slope and
Different ones.
different y-intercepts. So what you could do is check to see if slopes are the same. So if same slope, different y-intercepts. So there is a mathematical way that you can check to make sure that you have the right answer. Okay? All right, I think that's about it for today.